And for the talk today, it's Kaif Hilman.
Yeah, thanks for the invitation. I didn't have to press anything more, right? I didn't have to press anything.
No, I think we're
Yeah, thanks for the invitation to speak. So today I want to tell you a bit about joint work I did with Phil Instance on parameterized functional calculus. And just to put things into context, to go with Christine's botanical analogy, yes, in some sense here I'm going to tell you that I'm giving a not world-changing but sort of slightly new taxonomy to how things should be classified. And in some sense, homotopy calculus and equivariant calculus belong to one slightly bigger taxonomy class. And right, also I should also say that I'm a relative newcomer to the field of calculus, so I want to apologize in advance if I get overly enthusiastic with simple things. Impact this on my zeal as a new convert. Okay, so I want to motivate the whole story first. In fact, I'm going to give you two sets of motivations because it's a long story which I haven't even scratched the surface of the hard part. So I'm just going to tell you, what my dreams are in my true motivations, and then I'm going to give you another set of motivation, which is the fake one, which is what the talk is going to be about, because that's the only part that I can actually do something about. So the true motivation is that, in some sense, functional calculus is about organizing non-linear phenomena in category theory. And some of these cubes, at least to my eyes, the reason they show up is because, well, we've come to accept that linearity, passiveness is about like squares. And when you want to analyze like power functors, like you take your x and then you power it up n times, like cubes naturally appear. And that's sort of to my eyes why cubes appear. But in any case, this is what I feel I understand functional calculus is about. On the other hand, throughout the week, we've seen that there's in equivariant homotopy theory, there's like some other more exotic forms of multiplicative structures in the form of norms. And so it becomes like natural to dream that you might be able to create a theory to organize all of these things and treat them in the most native way possible. I should say that you can use ordinary calculus to analyze some of the nonlinearity of the norms, and this has been done as far as I know by, for example, Nikolai Konovalov. But there are some certain non-native aspects to this, which is slightly unsatisfactory. So that's the long-term dream. I'm very far away. In the equivariant example, this, as far as I know, has been first considered by Blumberg, who talked about the notion of G linearity. And then that was taken up by Dotto Moy, who did some other stuff about linearity before Emmanuel Dotto developed an almost fully fledged theory of equivariant calculus. This was the thing that Christine mentioned. Right, and the way I got into the subject was because I was analyzing the multiplicative norms of equivariant algebraic theory. And so it's too long to explain, but it's natural. I naturally learned in this subject. And so I hope that sort of if this long-term program can be, can come to fruition, then you should have interesting applications to equivariant algebraic K theory as well as Hermitian K theory. So, part of my hope for this talk is that, so I do want to give quite a bit of detail as to how the theory should look like. I want to give you a general feeling for what I think the shape of the theory should be. Okay, so that's the end of the true motivations. Here's the fake one, which is what the talk is about. So Dennis Nadin axiomatized the notion of Miller isomorphisms that we saw yesterday already, and multiplicative norms via this theory of parametrized higher algebra. I don't assume that people are familiar with this, so I'm going to review this in a bit, but sort of, in particular, what you can say with this whole theory is you can talk about parametrized stability, and this is defined in terms of the Miller isomorphisms and ordinary stability. So what he was trying to do was to somehow capture the essential features enjoyed by genuine G spectra for finite groups. So everything here should be about finite groups. Just for purely aesthetic reasons, there are like two sort of a bit unrelated conditions. You can ask, if you can find one condition to define what stability is. And the way I want to phrase this question is whether or not you can define in terms of suspension. Why do I ask this question? Well, here's a fact. If you are a pointed presentable category, then being stable is the same as your suspension endofunctor being a self-equivalent. So, there's kind of like a spherical feeling to stability because of this. And in equivalenting, this point become more, more pointed because this was actually how genuine G spectra first came about. They sort of defined it by inverting representation spheres before people talk about the But I mean, that was what they had in mind anyway. So from this classical thing, you can deduce the following probably meaningless statement now, namely that pointed G presentable category is G stable. I'll review all of this later. If and only the representation spheres act invertibly on it. So, you can be optimistic that spherical characterization of parameter stability can happen. And just to get a feeling for where this talk is heading, here's the vague theorem in its vague form, which I'm going to spend a lot of time trying to make precise. If T is a sufficiently finite and algebraic category, the kind of T that you should think about are the orbit category, let's say, the category that you're parametrizing over. And C is a pointed T presentable category, whatever that means. Then T is T stable if and only it is spherically invertible. The moment is just like word salad, but the point of the first half of the talk is to make this precise. At least we know where we're heading. Examples of this sufficiently finite algebraic categories are the orbit category for finite group, but also this category FED that appeared in Greg's talk yesterday. So these are the category of finite sets and surjections up to size D. And I hope at the end of the talk, I can give you one funny application of this theory to this FED. So it's like, application outside of equivalent homotopy theory. And the slogan of this talk that you should remember is that you can use Goodwillie calculus to systematically relate spheres to the notion of semi-additivity. This is sort of how it's supposed to go. And just as a meta slogan for how you should think about this talk, I think this ties in very well with this workshop because, on the one hand, we saw Christine's talk about calculus. And on the other hand, we saw like Mike's talk about equivalent homotopy theory. You can try to take the full guy. Find to be deep. The way you should think about my talk is that there's a map of some non-trivial connectivity. This is the legend or like a map for the entire talk. This is how we should think about it. Because everything is going to look quite abstract very quickly. But I want to remind you that it has something to do with equivariant calculus, which was something of interest that we saw two days ago. Okay, so now I want to review this thing called parametrized higher algebra. This definition is due to Bowie, Dr. Glassman, Naveen Shah. And in some sense, if you read their manifesto, their work was actually inspired by Michael's philosophy that you are supposed to try to equivalentize all the indexing diagrams. And this is sort of their higher algebraic implementation of this philosophy. I'm going to give you some words, and then in the next slide, I will explain how you should think about these words. So a small category T, which you should, as a mental model, just think of it as an orbit category, let's say. We say it is orbital if the finite co-product co-completion has got full back. So just think of finite G back. It is atomic if we track equivalences. It doesn't really matter what the precise definitions are. I'll tell you how to think about this later. For me, a T category is going to be an object C underlined in categorical species on T. And by cat here, I mean like, infinity categories and so on. So again, this sort of plays into Mike's philosophy that, there's this external and internal structures, and this is sort of the externalization of all this equivalent stuff. So instead of just looking at genuine G spaces, you look at genuine G categories. Similarly, you can talk about pointed T categories. This guy has an internal home object, which I'm going to denote what is.
What is finity?
Affinity is the finite co-product co-completion of T. So you free X. In the object category is finite G space. There is the internal home. Like this. As a matter of notation, for every object in V, I can slice the category T over V, and then this admits a forgetful map to T. I can restrict along this to get a functor from cat T to cat T P. And in the equivariant context, this is precisely the restriction functor, because the orbit category of G sliced over a coset G mod H is after all isomorphic to the orbit category for H. So you're kind of restricting H, G equivalent things to H. Okay, here's how you should think about this atomic orbitality word. What it buys you essentially is this double coset decomposition. So the word orbitality just says that, yeah, right, in general, you can try to take a pullback of two maps of orbits. It might not become an orbit again, but you're only, a finite co-product away from being correct. So sort of orbitality buys you that, when you finite co-product complete, you suddenly have pullback. Atomicity says that, so there's something we saw in Mike's talk this morning, namely if you set K to be H, so you take the diagonal pullback, you're going to find one canonical copy of G mod H in this composition. So if you've done some equivalent homotopy today, I hope this sort of convinces you that it's worth atomic orbitality is a good thing. Another example is this FED stuff. Just for some visual intuition, like, for the group CP, the orbit category looks like this, and so a CP category literally just looks like assigning a category for the subgroup CP, a category for the subgroup E, equipped with a CP action together with the different function. Here are some important examples. That will play a role, but yeah, you can generalize genuine G spaces to genuine T spaces in the obvious way. You can look at the species over T slice over V. Similarly, you can talk about genuine T spectra when you look at Mackey functors on this T sliced over T. And the sort of functoriality in T is given by various restrictions. So here, this is the reason why you really want to work in this parametrized world. Namely, this implements this philosophy that sort of you want to consider the G action on your indexing diagram itself. And I claim that using this technology, you can talk about the induction and co-induction functor as if they were actually co-limits and limits of a certain sort. So here's a precise way to say this. Suppose you have two T categories, J and C. Categorical species are, after all, like naturally two categories. So you can talk about adjunctions. And adjunctions are just fiber-wise adjunction. It's a diagrams valid in CAT, there's fiber-wise adjunction. Anyway, so for this J guy, you have a constant map to the point, so you can restrict along it to get a functor J upper star from C to fun JT. In nice situations, it has a property that it might have a left adjoint or a property that is a right adjoint. These things I'm going to call J co-limits and J limits. Here's the key example that you should keep in mind. Every object V inside T may be viewed as a T category via this embedding. I can look at the Yoneda embedding species, and I can further embed it into T category. And sort of co-limits and limits indexed by these kinds of diagrams, they are called index co-products and products. And the reason for this is because when you specialize to the equivariant case, V and you choose V to be G mod H, V lower shriek is the induction and V lower star is co-induction. So this is sort of, it's a way to implement this philosophy. Okay, now that we have defined index co-product and products in this way, we can now talk about semi-additivity. To do this, let me just say, if your P category is pointed, then by pointedness and by this atomic orbitality thing, you're able to construct a transformation from F lower shriek to F lower star, generalizing the transformation from induction to co-induction. This may or may not be an equivalence, but certainly it's called the semi-additivity norm. And if you've never done equivalent anything, then the way you should think about this is that, in a pointed category, you can ask if it has a property of being semi-additive. And this property is defined as the canonical map from X co-product Y to X product Y being an equivalence. This map is given by 1100. When you generalize that equivalently, you get the map from in to co-in. When you generalize that to atomic orbital, you get F lower shriek to F lower star. Using this, Nadine defined the notion of P semi-additivity, namely, a pointed P category is P semi-additive if this adjoints exist and the norm map is an equivalence, as you might expect. And we say that it is P stable if it is furthermore like fiber-wise stable. It is, after all, a diagram taking value in categories, and you can ask whether, for every object you get assigned to a stable category. Okay. Just to fix your intuition, let's look at some examples and a non-example. Consider a subgroup H inside G. Here are two examples of equivalently stable categories. You can look at Borel equivalent spectra, you can look at genuine equivalent spectra. These things are certainly fiber-wise stable because all of these guys are stable, but they are also equivalently stable because in equals to co-in. In the first thing, it's easy to show because spectra is semi-additive. On this side, it's either an easy exercise or a not so easy exercise, depending on how you define the model of genuine G spectra. In the not so easy regime, where you've defined things in terms of inverting representations here, this is what's called the isomorphism, because he was the one who proved this result. In fact, he proved it for compact B, but it's more general, but today's story is only about finite proof. So this is called the isomorphism. Here's a non-example, don't make the pitfall. This spectral coefficient, these things are not G stable. Because they are, even though they are fiber-wise stable, you don't have this property. And in fact, it's a matter of historical remark, this was actually somehow secretly the reason why genuine G spectra were invented in the first place. Because you wanted to find a category for which you can say that smooth closed G manifolds are equivalently concrete duality. And without in being equal to co-in, you have no chance for that to happen. So you want to kind of find a world for this to happen. And I think maybe Siegel was the one who sort of suggested what genuine G spectra are. Not if I remember, but yeah. So this somehow this genuine G spectra came as a fix to your first erroneous guess. Right. So that's all the basic review that I want to do. Are there any questions so far? So I want to give some more definitions, but this is where our work begins. I want to tell you about cubes. So this cube is actually how I got into this subject, because as I was considering this multiplicative norms on K theory, for reasons I wouldn't try to explain now, you have to somehow deal with cubes, like equivalent cubes. And these are really hard because one trick that we take for granted in life is that we can curry, namely math from x times y to z is the same as math from x to math from y to z. This allows you to do a lot of cubical induction based on the size of the cube. Equivalently, you can't do this. So you always have to come up with coordinate independent cubes. So this kind of structures have been a bane of my life since, for a bit too long, but, but suppose you have a map infinity, think a map of parameters. Again, I have this restriction co-induction junction associated with this. I define the parameterized F cube to be nothing but F lower star of delta one underline. So delta one underline is just an object here given by the constant diagram with value delta one. And then F lower star delta one is whatever it is. But the point is that when you work over this base category being atomic orbital, you can check that this F lower star delta one is at least given fiber-wise by cubes of various dimensions. And so that sort of really justifies the word F cube. And because cubes in various dimensions, you can imagine that there are objects called 0 and 1, which are the initial and final objects in this thing. Here's the interesting example to think about. If I look at the map from G mod H to G mod G, F lower star delta one is nothing but the index product of delta one. Meaning to say, you take delta one, you take product of G mod H many copy, remembering that it was a G action, commuting with different directions. Another way to say this is the whole set of subsets of G mod H, all subsets, and that's where the G action comes from, right? Because if I just look at a random subset, I can act on it, it's going to give me another subset. So you have the G action on the entire diagram itself. Okay, so yeah, I hope this is enough. Now you can use these things to define parameterized suspensions and loops. And I'm going to show you one maybe scary looking thing, and then I'm going to try to motivate it. I define a parameterized suspension as a composite of a right-hand extension and a colimit. This shouldn't be unfamiliar to you because this is how you define suspensions. Right? You start with an object, you produce the span which is given by x00, and then I take the colimit. And x00 is also known as right-hand extension. And similarly, if you take an n cube, you do this procedure, you're going to get the n minus first suspension of the object x. So it's also self-explanatory, and then you dually can define F loops. For example, in the equivalent case again, this F suspension is going to give you smashing with the 1-point compactification of the reduced regular representation associated with finite set G mod H. In particular, let's just take stock of what's happened. Let's say you're looking at the group C2, and I take the C2 index product of delta 1. So I have a square. Where I'm allowed to I remember that this has a flip. And so when I do this right-hand extension, I remember my diagram like this. There's a thing like this. And when you take the parameterized coordinate, what you're going to get is the sign suspension. So, yeah. Right, so that's that. Now I'm going to introduce one more word before I can at least say precisely what the theorem says. The category T is said to be locally short if T sliced over V has finite length for all V, i.e., the longest chain of non-equivalent morphisms is finite. Example of this is the orbit category. In fact, this is globally short because the category has finitely many morphisms of the orbit. But an example which is locally short but not globally short is a simplified form of the category that you see in global homotopy theory. Namely, you can look at the category whose objects are BG, where G is a finite group, and morphisms are those which induce injections on pi1. For this category, when you slice it over and chosen BG, you are going to get precisely the orbit category. So you see, you have this large category which sort of locally kind of short. And then the statement of the result now is that if I started with a locally short atomic orbital thing, And C is a pointed T presentable category. So I didn't define T presentable, but the way you should think about this is just a T category, roughly speaking, which are fiber-wise presentable, like spaces and spectra and so on. Right. So it says this, then C is T stable in Nadim's sense. So this means T semi-additive and fiber-wise stable if and only if it is spherically invertible, i.e., for all these F's, the suspensions become self-equivalences locally, these are local conditions. So yeah, this is the spherical characterization I'm talking about, which sort of specializes to the equivariant case, let's say. And then, as a spoiler, sort of the reason I don't know if this is necessary, but at least the only proof I can think of is that I needed this local shortness to do some induction, some parameterized cubical induction. But we'll come to that. Yeah, so right. If you've never seen calculus, okay. If you've seen calculus, you can switch off brain for one slide. But if you haven't seen calculus, maybe this is the one slide to take an idea of it. And this has nothing to do with parameterized or anything. They say the following thing: if you have a pointed category with pushouts and pullbacks, and suppose the suspension endofunctor is an equivalent, then the category C is semi-additive. Yeah. And I'm going to show you an overkill way using calculus to prove this result. So the way you do this is as follows: by Goodwill's magic formula that we saw in Christine's talk on Monday, if the functor is reduced, then P1 of F has this specific formula. Now, if I just plug in F to be the identity functor, I'll see that the identity to its first excited approximation is an equivalence, because I've assumed that suspension is a self-equivalence. And so the suspension loop adjunction is even an equivalent, so the adjunction units are equivalent. So all these maps become equivalences. And so you see that the identity is one excited. One excited. And so then you can look at the square that we also saw in Christine's talk today, I think. Namely, you have this push-out square involving the co-product. But because identity was one excited, there's also a pullback square, i.e. X co-product Y is also known as X times Y, or as semi-additive. So this overkill, I say this as overkill because you can prove by hand this fact. And in fact, this is what Lurie did in chapter 1.4 or something like this in higher algebra, before he introduced Goodwill calculus in chapter 6. So you can do this by hand. It's hard, but you can. But sort of, this.
Is it equivalent? Is it an even only? Even like the one that five and even only?
No, I don't think so.
No.
I don't think so. I did ask a lot. I've asked some very clever people. I didn't think.
Well, yeah,
I don't think so. No. And this is actually a source of a lot of my problems, which I probably won't say too much today. Right, but I just wanted to appreciate how magical this formula is. This, if you, having spoken to some experts in Goodwill calculus, sometimes they ask themselves if you actually needed to know that. Yeah, sometimes you ask yourself if you actually needed to know that the formula looks like this, because sort of by adjoint functor theorem reason, you can often deduce that the excited approximation exists. And this is an instance where you really needed to know how the formula looks like. If I just knew that the adjoint exists, and I'm not really sure I'm going to argue. So this, hope this gives you some appreciation as to how deep these ideas go. Okay. So I have sort of reviewed this parameterized thing. I've given you a bunch of definitions. I've at least stated the theorem in the most precise way I can now. So now I want to, again, the general strategy is clear, right? So I told you like an ordinary calculus for strategy. Now I just want to see calculus my way to do it. And so this is where we have to introduce parameterized calculus. I should say that if you are aware of this work by Robin Stoll, who was a master student of Immanuel Otto when he wrote his master's thesis, he has a paper on like functional calculus for non-cubes. Meaning to say, you can develop calculus quite formally if you just look at certain concepts with some nice properties. The way we phrase things is very much inspired by the way he did it, so the useful language, but our basic objects are quite different because, at least to me, I found his basic definition a bit hard to use and hard to use because sort of he was aiming for maximal generality. The definition I'm going to give you today is general enough to cover all the examples that I care about, and which also afford very clean and easy proofs. And this is the notion of accessible proofs that we talked about now. Okay, so a T4 set is nothing but a T category which are fiber-wise a 4 set. So examples of this are this parameterized F cubes, because I already told you that they're fiber-wise cubes. We say that it's complementable if it is a fiber-wise distributive, meaning to say you admit finite co-product and product and this distribute in the way that you expect, and it's complementary in the sense that for every object in L, you can find its complement. So you can find another object which co-products to the final object and product to the initial object. In ordinary cube land, I hope it's not so surprising, because if you view it like, I don't know, subsets of a finite set, you can just take a subset, take its complement, that's its complement.
Sorry, by object and L, do you mean in more of a fibers or like a co-partition set?
Yes, yeah, all of these things are fiber-wise. Yes, thanks. Yes,
They don't show many uniqueness for the components or
no. No, I don't understand it, but no. And now an accessible poset is the datum of the following thing. You have a complementable L equipped with a downward closed sub-poset, which I call L and a half moon. And I follow Robin's notation for this, the L half moon. And then I'm going to write L cert for the sub-poset, which is basically everything, but you puncture away from the initial object. Right, so this is a bit abstract, but let me draw you some examples, then you get a feeling for what's going on. Examples for us, which should be important for us today, are the following. Suppose you have a map of finite T sets. You can look at the parameterized F cube, but you can give it two different accessible poset structures. Namely, you can look at the thing which is just punctured away from the final object, or you can look at the thing which is so this F lower shade, you should think of this as like finite co-product of points, and then I just adjoin the initial object. So I'll draw a picture so that this becomes natural. So you can think of this F lower shade as like the singletons in the cube. So look at it. You can look at this picture. I hope you can see the color. So sigma F is just everything which is, the red part of the this half moon thing. So sigma F, you look at the cube, but then you puncture away from the final object. Phi F is where you take everything which is distance at most 1 away from the initial object. And then L circ is where you puncture away from the initial object. I just throw away this bit. Hope that's clear. This should be something, by now a familiar friend, because this is the kind of thing that you use to define strongly co-Cartesian cubes. Because remember, strongly co-Cartesian cubes are defined as cubes for which all the two-dimensional faces are pushed out, aka is left unextended from wherever this is. As a mnemonic, I mean, the reason I call it sigma is because it has something to do with spheres. And this phi f this stands for span, because this looks like a fan shaped thing. So if there's like, too many overwhelming symbols, you can just go back to this mnemonic. Okay. Now using this very abstract formal language, you can define like parameterized excisiveness. Suppose you are given an excisable four-set, and suppose you have an L index diagram in C. We say that it is sigma co-Cartesian if it is in the image of the left-hand extension, and it is Cartesian, sigma Cartesian, if it is image of the right-hand extension of this subcategory. So again, specializing to the ordinary calculus world, if I look at one of these phi f things, then sigma co-Cartesian is precisely being a strongly co-Cartesian cube, when the left-hand extended from the half-moon subcategory. And being sigma Cartesian is just saying it's linear diagram. Yes.
So the sigma Cartesian doesn't.
No, yes, right, exactly. So this maybe it's not so good notation, but you want to remember that they always come in pairs. So yeah, right, exactly. Sigma Cartesian doesn't depend on sigma; it just depends on L actually. So now you can just define a functor to be sigma excisive if you take sigma co-Cartesian thing to sigma Cartesian thing. So very cheap definition you can make. And again, like, specializing the case. Suppose I consider the map from a finite, a disjoint union of n plus 1 points, going to the point, I plug into this machine, I get precise, and I look at this phi f things, I get precisely the notion of strongly co-Cartesianness, and so this definition specializes to the notion of n excisiveness that we've been seeing this past few days. Okay. Right. So now I want to state the, the first basic main theorem. And for that, I'll need this language that we've already kind of seen in Thomas's talk, in Connor's talk, and also in Christine's lecture. Mainly the notion of differentiability. So if I have a P category D and I have an excitable four-set, then I say that D is sigma differentiable if it admits this L sub limits and sequential co-limits and that these things commute. So essentially, I mean, differentiability was defined as the fact that sequential co-limits commute with finite limits. But here I want to be specific I just need to be specific on which types of limits I need to commute with, and I just say L sub limits. And as you expect, the basic main theorem, if you have an excitable four-set and D was sigma differentiable, then the inclusion of sigma excisive functors into everything admits a left adjoint with a nice formula. And as I said just now, so the real content of this result is this word nice formula. In most cases that you ever care about, you kind of know that the adjoint exists. But it's really good with this miraculous formula that you're really after to set up entire theory. All right.
Good. If the left adjoint is always left exact in this case.
No. Okay. This is another bane of my life, which the slogan is that it's very hard to know if a G category is G compact. In the same way that it's hard to know that a genuine G space is G compact, apart from exhibiting a finite GCW complex structure on it. I mean, how are you ever going to know if the space is G compact? You can check if each fixed points are compact, but that doesn't guarantee that you are G compact. It's the same categorical problem, and you're sort of reduced to knowing that the G cubes or P cubes, whatever it is like a P finite category. Yeah, that's sort of the reason. Right, so some comments for the experts, or I should say, I'm really glad as to the way that this this workshop was structured because I can basically model a lot of things because we've seen a lot of things from Christine's talk as well as my talk. And now I feel like I have the right to say that whatever Christine told us basically works. Which again, it's a testament as to how crazy good this idea is. It just is so robust and it just works all the time. If you just know what adjectives to put on your object. Right, so some comments for the experts. This is probably the most technical part of the talk. Right, the whole point of this complementability, blah, blah, is that for every object in your post set, you obtain a smashing localization and co-localization of your post set. So Lx is defined to be the essential image of taking product with X. This admits a left adjoint given by co-product with the initial object and the right adjoint given by co-producting with the complement. Why do I like this kind of thing? I like this kind of thing because this gives me very easy proof of many things. As if you look at the proof that it really gives, oftentimes, so the only trick I know and the only trick I use in all of these things is the following. Namely, X, you know that this guy is left adjoint to this guy. And so pre-composing reverses the adjunction. So upper star reverses the adjunction. Because of this, you see that X map, when your left can't extend along this middle map, it is given by restricting along this guy. Basically, you do this kind of trick 10 times, everything just falls down. So there's the reason why you want this kind of complementability, is that cofinality arguments are, in general, tricky to write and tricky to read. When you put this kind of assumptions, which is sort of more or less all that you ever needed in all the examples that care, you have this adjunction on the level of post sets and all the proofs look like this. Right, so for example, it allows one to prove this kind of technical statement. So it doesn't matter if you don't read this, but I should say this is sort of this kind of thing that we saw in Christine's talk, namely to construct this kind of excited approximations. Remember, if we were given a diagram chi, we define an auxiliary diagram given by chi sub v, which when you evaluate at u is defined to be chi of v union u. This is what this procedure is doing. And you need to check this kind of properties and sort of everything just falls out by adjunction, basically. Okay. And so the key lemma, as also something we saw on Monday, when you look at this telescopic co-limit, these things are going to be intertwined or interleaved by the sigma Cartesian things. And because I've assumed that I'm sigma differentiable, when I take the sequential co-limit, everything commutes and I get a sigma Cartesian thing. That was what we saw on Monday. Here's the kind of interesting, well, I don't know if it's interesting, but it's sort of how you get these towers in when you say things in this way. When you get tau, in fact, this equivariant tree or whatever it is, any kind of graph, you get out whenever you have a some sequence of compatible excitable post sets equipped with some objects. So if I have a tower of excitable post sets for which Li is the same as Li plus 1 meshing localized as some element Ai plus 1, I'm going to get this tower. So for any kind of smashing localization of post sets, you get this tower of excited approximation. So that's how these towers and graphs and whatnot, this is how they show up when you say things like this. Okay, so that's all the general calculus theory that I wanted to say. Hope that's sort of reasonable. And in the last section, I want to give a sketch proof just to tie it together of this result. So remember our sort of target theorem or whatever is this thing. Namely, you want to give a spherical characterization of Nadine's T stability. I claim that if you know that you are T stable just by general blah blah, you know that it's spherically invertible, so I don't want to talk about that. The hard part is the reverse direction. And so that's what I'm going to prove or sketch the proof of. So I'm only going to show that if you're spherically invertible, then your T stable. I'm only going to argue that your category is going to be T semi-additive. Because fiber stability is also kind of easy to forget about that. Again, by the theorem on the excited approximation, if F is reduced, you're going to get this formula for the sigma F excited approximation looking like this. So this, there's loops and suspensions appear. Okay. So by the same argument that we already pulled up just now, you're going to get that the identity of C is sigma F excited because you already assumed that C was spherically invertible. Now, maybe let me make this comment after this, but in particular, just by almost general topology, like sigma F excitedness implies phi F excitedness. Let's review why. If you're left-hand extended from the span, in particular, you're going to be left-hand extended from everything in this thing. And because you assume your functor to be sigma F excited, when you hit it with a functor, you're going to get a limit diagram. So, clearly kind of like if sigma F excited functors are in particular like phi F excited. Now, the key lemma, which I'm not going to explain the proof of, is the sort of parametrized cubical induction. This is where the word local shortness comes in. And it says that if your functor is reduced and it is phi F excited, then your functor is T semi-additive. Meaning to say it takes index co-product to index product. It is the key sort of cubical thing that I didn't know how to run away with. One has to do this. And as I said, as I pointed out earlier, these kinds of arguments are a bit trickier to do in the general setting because you cannot just say, oh, induct on the size of the cube, because you cannot choose spaces. Because imagine if you have a cube with a G action, if you've chosen a space, then the space starts moving around. How are you going to do any induction? So you have to come up with sort of coordinate-free tools for all of these things. Anyway, once you know this fact, identity is sigma F excited, and so is phi F excited, and so is T semi-additive, and so is C is T semi-additive. How these things fit together. The comment I wanted to make was, I don't know, maybe this is again an overkill, but this sort of demonstrates the utility of setting up such a flexible abstract language because it allows you to relate different notions of excitedness which have to do with different kinds of things. See, sigma F excitedness has something to do with the spheres. Phi F excitedness, by this lemma, if you believe me, has something to do with semi-additivity. Just by diagrammatic reasons, this link is rather clear. And so, when you set things up so flexibly, you get to relate different types of notions. Yeah, I mean, that's sort of the point of setting up this language like this, because you can pull off this sort of proof. Okay, in the last two slides, I want to turn to less serious things. The first is a funny corollary. I mean funny in the weird sense. I don't know if you find them humorous. And it is that, okay, so let me just remind, so there's a theorem of Glassman which says that the category of de-excited functors which are reduced from compact spectra to spectra is given by spectral Mackey functors on the category FPD. So this is the kind of result which is like, what Greg called like Pirashvili, Helmstutler and Balder type result. I mean, it's not exactly, but it's these types of results in that ballpark. So in joint work in progress with Toby Bartel and Nikolai Konovalov, we provided a symmetric model enhancement of this equivalence of Glassman. And in fact, we've even enhanced even more, we've got an entire parametrized equivalence of this. I wouldn't have the time to say about that, but this parameterized equivalence, I should say, at least, is related to this old observation that there's a very tight dictionary between genuine equivalent homotopy theory for finite groups on the one hand and good Willy calculus on the other. And you'll hear more from about this tomorrow. So I'm going to say much more. Anyway, right. So using all of these things, using this theorem as an almost immediate corollary, you get the following result, which says that there's a symmetric monoidal equivalence from this guy to pointed presheaves on FED after you invert the representation scale. So this is kind of like a calculus version of this, representation scale. And this series, of course, I hope you can guess, these are coming from the appropriate F suspension, this parameterized suspension. And the reason I find this funny is because first, you're kind of using parameterized calculus to prove something about ordinary calculus. Yeah, that's it. I don't think this is humorous, but it is certainly. The second funny point is that there's something going on which I don't understand. Namely, if you remember from Greg's talk, he said that de-excisive functors from finite pointed spaces to spectra is given by functors from FED to spectra. But somehow, for some weird reason, when you stabilize in the source, suddenly an op appears. After you invert the representation sphere or so. So yeah, I don't really know what any of this means. I don't know how this is related to what Greg talked about, but I feel like in some ideal world.
Is there an easy description of the functor from left to right, like functor
From
direction? Like given an n-excited functor, what do you associate to it?
Yes, that's a good question. Essentially what it is cross effect. Cross effect.
Cross effect or co-cross effect?
Yeah,
Cross effect you would expect.
yeah.
Maybe it sounds like you're taking the co-cross effect.
Yeah, so right, because right.
Yeah, so in that other result that you mentioned, you take the cross effect, which is covariant, but somehow you want to.
Yeah, right. Okay. Yeah, I didn't think of it because I'm so used to thinking about the Mackey functor side, for which everything's stable, so you take cross back, co-cross effect doesn't make a difference. But yeah, I suppose when you want to make this connection to unstable, then the secretly taking the co-cross effect. Yeah, who knows? Yeah, thanks. Maybe let's solve something. But and the third thing I wanted to say was that these representation spheres, I actually don't have any interpretation for them. But these are numbers that come up very naturally, and these are numbers which are secretly related to the numbers that you saw again from Greg's talk yesterday. Something to do with counting surjections from M to M or something or other. This is sort of what the dimensions of these spheres are. So I don't know what these things are counting, but it seems to be interesting. Anyway, so that's the funny thing. The last slide is that I want to do some meditations and kind of engage in some kind of a wordplay which might be totally pointless. Namely, I want to talk about geometry of semi-additivity. So we've seen from Connor's talk that there's a notion of semi-additive geometry. I guess it is now this famous, Brave New World of Marlin semi-additive geometry. But sort of, that's a very high-minded thing, and I'm a person of more pedestrian persuasion. Whereas there, when you talk about semi-additivity, it means like one semi-additivity, the norm map from orbit to fixed points. And to him, geometry means some kind of a tangent plane on the purple sphere. Whereas for me, geometry, I'm going to mean geometry, and semi-additivity just means zero semi-additivity, or rather T semi-additivity for some finite set. And the picture I'd like us to think about is the following. What is this picture? This is like an embedding of a finite set of points in a sphere. And this picture is essentially how you prove the Bird-Millar isomorphism. So what you do is the following. You take a finite G set, you put it in a large representation sphere, which you can do. And then you can kind of perform the Pontryagin-Thom collapse map, collapsing everything outside of a neighborhood of this point. What it buys you is a map from the representation sphere, this big representation sphere, to some equivalent bouquet of spheres, where the equivalent, the groups also commuting this bouquet. Long story short, you use this kind of construction to construct the datum witnessing that G mod H itself to a genuine equivalent homotopy theory. This is how this Z thing goes. And in fact, this proof is it's much more general. You can do it for compact D groups, but for today, I'm good. I can ask, but I just gave you this proof using calculus, which seems to just forget all of geometry. I claim that we forgot a lot of geometry, but not everything. Some feature of this proof still survives. Namely, I basically looked at the embedding of the singletons in the cube. So if you are very, very loose with your analogy, cubes are spheres. And punctured cubes are spheres. Whereas the singletons are your way of embedding these finite G sets into a sphere. So you can kind of think of cubes as like a categorified sphere. And I can't make any of this precise because it probably can't be made precise, but I would like to suggest that, thinking about cubes is a good thing because could be that cubes provide you an entry point for stable homotopy theory to talk to post-set combinatorics and to geometry. So on that note, thank you for your attention.
Question, so if you have some categories, key categories of pointed or semi-additive, is there some way to invert the spheres to force it to be spherically invertible?
Say again?
Do you have a procedure to spherically
Yes,
make
yes.
it spherically invertible?
Yes, yeah. There's some parametric thing you can say, but yes. Short answer is yes. I think this was done by Bastian actually in his thesis. Bastian Knossen, so yes.
So I had a question related to Glassman's things.
Mhm.
So, spectral Mackey functors on COM, that should be like some type of genuine parametrized thing, related in spectra. So I have whatever transfers are, right? But then, right, as you mentioned, that there's also some type of COM pre-sheaf classification of polynomial functors spaces to spectra, but that doesn't have transfers. And I wonder if you have any interpretation of why, if I go spectra to spectra, the polynomials are some type of genuine thing. Whereas if I go top to spectra, that'd be like I think the super naive thing, if I understand correctly.
Yeah, again, as I said, I'm very new to this, I actually don't understand what's going on, but I think this has something to do with what Greg said, namely the confluence of co-cross effects and cross effects in the stable context. I think sort of the reason, the fact that there are two different notions when you work unstably means that you don't get maps in one way.
I think the target just needs to be stable, as far as I know, to get the.
Yeah, exactly. So right. So I'm not sure. And
Okay.
yeah. But I think it seems to be this seems to be what's going on, but I don't know. Sorry. Yes.
So we don't worry about the fiberized stability issue. The proof that you give, just give you a nice presentation for incomplete semi-additivity. Like if you have just a collection of orbits, you use this for only the permutation modules associated with it or the cubes associated with it.
Mm-hmm. So what was the question?
Oh, I'm just asking, does this that argument extend to give you a spherical presentation for stability with respect to some incomplete system?
Yeah, so right, so this was at some point still and I got lazy. He asked me whether you can do this incomplete stuff because you don't have to invert all regular representations. You can invert some things in incomplete way. We believe that you can do that by came finicky to kind of state it, to formulate it, but I think you can get something like this, invert some spheres, as long as you don't invert the big regular representation here. You can kind of build in transfers, but not all of them, yeah. But I'm not doing nothing.
We fall aside. Let's thank Mr. Jan.